Our second example is going to be looking at fluoride and cavities and looking at different fluoride treatment levels in municipal water supplies. That's one of the public health measures that gets put in place in various cities to try to reduce cavity levels, because there's evidence that including fluoride treatments will help reduce cavity levels. What we have in this example are several cities, and their fluoride treatment levels have been classified into low, medium, high. So we're going to have 3 groups. And then what we also have are data on the number of cavities per 1,000 of young adults. So what we're going to do is just try to determine whether the level of fluoride is independent of the rate of cavities in young adults. So read the data in and take a look at what's inside of it. Okay, we got fluoride levels, cavity rates, and then we would want to take a look at the fluoride levels and just make sure that we actually have all those 3 levels that we mentioned in the S&D. So we got medium 15 towns, low 15 towns, and high 15 towns. And then we might as well go straight to our plot. So we're going to use our cat plot, and X will be the fluoride level. That's the categories, and then the Y values will be the, pardon me for a sec, comment that. Right, we're not done yet. Cavity rate per 1,000, we're going to copy that in explicitly. There we go. And why did not like that? It did not like that because we did not include what data to actually use with that plot. There we are. This looks like it's got some stuff going on. There's a pretty wide distribution across the 3 towns, but it does look like the means will be different even relative or on the scale of the variations we see here. Again, we can do a box plot if that's more your thing. And yeah, it seems like if we have low fluoride in a town, there's a significant, there is definitely a larger rate on average of cavities. And what we're going to do is test whether it's significant or not. So we're going to do our same thing here. We're going to do our stat and our p-value equals, this one I honestly can't remember. We're going to copy all that. We're going to copy this whole jazz this time. And we're going to just update this with fluoride and put it in all 3. And there's only 3 data sets, so we only need 3 of them. And before I forget and get another error, I'll delete the data set 4 from that list. And then the options were simply low, medium, and high for this case here. High. And then the cavity rate per 1,000 was the continuous variable. All right. For the low fluoride level, grab all the data and then report all, specifically the cavity rate per 1,000, store that in data 1, medium in data 2, high in data 3, and then use those 3 data sets to calculate a one-way ANOVA, which does a comparison of the means. And so we get a 0 value here, 0 down to 2 decimal places. One of the things you can do is add more decimal places. The better way, especially for p-values, which tend to involve exponentials when they're more extreme, is just to change this to e exponential. And then we see, 4.8 whatever times 10 to the minus 7. Definitely small. So let's take a look at our results and discussion here. I'll just grab that here. And so for this one, the results and discussion is the null hypothesis is that all towns have the same cavity rate independent of the fluoride treatment level. And is that true here? If that were true, we would see this difference in means. Well, it's 10 to the minus 7, so basically 1 time in 10 to the 7 times. I got this fancy here. I got little dollar signs. Let's see how that does. Yeah, nice. 1 time in 10 to the 7 or 10 million ballpark. That is very unlikely. Given that result, we would, as a result, that is so unlikely, we again have, in principle, 2 choices. We can think the data's flawed somehow and not believe the data collection, but here we have no evidence for that. So the only other tenable option is that we would reject the null hypothesis. It doesn't seem credible, given this data, that the means are all the same. However, there's a follow-up question, which is, well, okay, so all three means are not the same. So not all three means are the same, but are all three different, here's the catch, pairwise from each other. That's called a post-hoc test. We will do a post-hoc test for that. Actually, better yet, we're going to do a post-hoc test to identify those pairwise means that are actually different. All right. So just looking at the data set here, our intuition tells us that for sure low is different from medium, low is different from high. One of the questions that's less obvious is whether medium is different from high. Again, looking at the wide range, we can see there is a numeric difference for sure. What we're looking for is a statistically significant difference between these two, given how wide the range is in each of these groups. Is this difference between medians/means significant given how wide the range is within the groups? And we don't know, so we pull out the statistics to help us assess that. Now the test we're going to use for that is called the Tukey, from the person who named it, HSD test. And what does that actually stand for? It stands for the honestly significant difference test. Again, there's so much good probability and statistics going on here. The key thing here is that it's easy to fool yourself with multiple tests and statistics. So the word honestly here is taking care of some of the heavy lifting for you, so you don't get accidentally trapped into thinking differences are real when they're not. So enough to say that the Tukey HSD is what we're looking for. Now, this is, again, knowing there's another layer here. This will be provided for any tests, of course, so you don't have to keep looking it up yourself. We're going to be using a related statistics toolbox, statsmodels.stats, and multi-comparisons. So if you think of what we're doing here, we're doing multiple comparisons between different means. So that's what we're going to be using, and we're going to import the Tukey, pairwise Tukey HSD. All right, I'm going to just make sure that runs, and that did not run because I have a typo in how to spell multi. There we go. There we go. And just so we can, again, see what's happening here, we're going to look up that pairwise Tukey HSD. So, and groups. So calculate all pairwise comparisons for the Tukey HSD with confidence intervals. Lovely. The NDOG, I think, is meant to mean endogenous. I'm not quite sure why that was the phrase they picked, but anyway, the response variable. So that is our cavity rate per thousand. And the groups is an array with the group labels, can be strings or integers. That's our fluoride levels. So as a minor bonus, we should do that one more time and figure out what the return values are. We're going to get a result, and we're basically just going to print that. It's going to have a whole bunch of data in it. All right. The surprising thing is, for the post test like this, where we're comparing all the pairs, we don't actually have to break up the data. I don't know why they haven't structured it the same way in the input, but there it is. So let us do this. We're going to call this results equals that pairwise Tukey HSD, and the endogenous thing is our data set with the cavity rate, and the groups are our data with the fluoride levels. So all the continuous data goes into the endogenous, and the groups are defined by the fluoride levels. And really, that's all we need. Now what we're going to do is add a little print statement at the end, and we're going to show what those results are. And let's call it the Tukey result, just to make it a little more distinctive. All right. Now this is typical of any more modern statistics, is to get a whole pile of data back. Let's walk through it. We have three groups, low, medium, and high. So what you're going to see here is every possible comparison between any two groups. So when we compare the high fluoride group to the low fluoride group, what you see is a difference of 42 between those two means. Just going up the graph to see where that ties in. Actually, let's bring this graph right down beside us here so we can do them both side by side. There we go. Perfect. The high to low, you can see the difference here is about 40-ish between the means. Well, again, it's medians, not means, so we get a little variation there, but about 40 between those two groups. Okay. From low to medium, we get a minus 35. And all that means is going from low to medium, we went down. Going from high to low, looking at this group, then this group, we went up by 42. So the only difference in the signs is just the essentially random ordering which of these two pairs comes first. But the way to read this is when going from the high to the low fluoride groups, the mean difference in the cavity rate goes up by 42. Going from the low to the medium group, the cavity rate goes down by 35. The only two important columns for us are the p-adjusted and honestly the more easily read reject column, or reject the hypothesis thing. So a difference between high and low is 42 cases per thousand, and that p-value is so small, it's below 0.005, our usual cutoff, 0.05 rather, and so we would reject the null hypothesis for that. So that would mean, yes, there is a difference. We think there is a difference between the high and the low cavity levels. High and low cavity levels are significantly different. Likewise, the low medium also gets rejected, and p-value is small. It's a big difference of 35. So the low to the medium are also significantly different from this test. The intermediate case is comparing the high and the mediums. There is a difference. You can see it right there, the difference between the means, but it's not enough given the variation within the groups to say that you can really treat that as a real difference. So whether a city treats their fluoride levels with a medium level or a high level of fluoride, you get statistically the same difference in cavity levels. And that would be our conclusion here. So concluding, there is a significant difference. There is a significant difference between, and here it's probably nicer to put bullet points, low fluoride and medium fluoride. Bear with me on the typing here. And low fluoride and high fluoride levels. In terms of the resulting cavity rate per thousand. The difference in cavity levels between the towns with medium and high fluoride levels, however, is not significant. All right. Not significant. There we go. Now, this is a lovely intro stats answer. In my mind, it's always insufficient. Statistical significance is lovely, but I think it's also helpful to put the scale on here. How big is this difference? So they're different, but how different? So this is a rate of low to medium. We would have around 35 fewer cavities per thousand. That is much more helpful. And this is around 42 fewer cavities per 1,000. That at least tells you how big is this difference relative to reality. So in the real world, how much of a difference is this? And of course, there's this internal conflict of, well, if it's different between these two, so one's 35, one's 42, what do we mean about these not being different? Because clearly they're different by 7-ish. This is just, we cannot reasonably say that that difference of 7 that we capture in between the medium and the high levels is something we could rely on and expect to see again if we were to repeat this experiment. And again, that's why we would put averages or approximations here. It's around 35, it's around 42. That's a reasonable distance or difference to capture. And that is essentially the end of a full analysis of a difference of means between multiple groups, where there are some significant difference between pairs, with a lesson that we always approach this as a 2-stage process. We look at, well, 3-stage. We always look at the data first, try to figure out what's going on. Then if we recognize that we want to do a difference of means here, and we have more than 2 groups, then we have to use an analysis of variance, or ANOVA, for difference of multiple means. And so we do that analysis and get a p-value. Only if that p-value is significant, in other words, saying there is some difference of means, they're not all the same, then we can do this post post-hoc analysis with the pairwise Tukey HSD and identify which particular pairs are actually different. In the original example, we saw where the one-way ANOVA didn't come up with a significant p-value. Then we were done. We just said, well, there's no difference between these means. Why would I investigate any further? So just be aware of that contrast. And with that, we'll move on to a case study.